All right, so today we're taking
Welcome
a deep
to
dive
AI
into
Podcast,
quantum computing.
New Tech, your
I know
ultimate
it's a
destination for the
topic
latest
that's
and
generating a lot of
greatest
buzz
in the
these
world of
days, and
technology.
honestly, it can be a
Hosted
little
by an
intimidating.
intelligent...
But I promise we'll break it down in a way that's approachable and even, dare I say, fun.
Exactly. This is a fascinating field that has the potential to completely revolutionize how we solve problems.
Yeah, and to help us navigate this complex world, we've got some great resources lined up, excerpts from Wikipedia and some articles from IBM and Google Quantum AI, the heady hitters in the quantum realm.
You know, what's really exciting is that quantum computing isn't just about building faster computers. It's a whole different paradigm. We're talking about harnessing the principles of quantum mechanics to tackle problems that would take classical computers, even the most powerful supercomputers we have today, thousands or even millions of years to solve. And potentially, we can do this in a matter of minutes.
Okay, now that's a bold statement. Thousands of years down to minutes. That's some serious speed up. So, before we go any further, can we just back up a bit? What exactly is quantum computing? I mean, it sounds like something straight out of Star Trek.
You know, it does have that futuristic feel, doesn't it? But the ideas behind quantum computing have actually been around for a while, going back to the 1980s. Brilliant physicists like Paul Benioff and Richard Feynman, they were the ones who first imagined using quantum systems to perform calculations.
So they were thinking about using the very laws that govern the subatomic world to build a computer that could, understand that world.
Precisely. And this idea leads us to the concept of quantum supremacy. It's the point at which a quantum computer can demonstrably outperform any classical computer on a specific task. Now, whether we've actually achieved that milestone is a topic of debate. Google made headlines back in 2019 when they claimed to have achieved quantum supremacy with their Sycamore processor.
Right, I remember hearing about that, but wasn't there some pushback on that claim?
There was. IBM, in particular, challenged Google's assertion, arguing that classical algorithms could still be optimized to perform the same task, just maybe not as quickly.
Ah, so the race is still on then. But just to be clear, right now, in 2023, are classical computers still the top dogs for all practical purposes?
Absolutely. Quantum computers are still in their early stages of development, but the potential is enormous, which is why there's so much excitement and investment in this field.
Now, you mentioned quantum mechanics a couple of times, and to be honest, it's always been a bit of a mind bender for me. I mean, it's like the universe operates by a different set of rules at the subatomic level.
You're absolutely right. Quantum mechanics governs the behavior of matter at the atomic and subatomic levels, and it's completely different from the classical physics we experience in our everyday lives. And to understand how quantum computing works, we need to grasp a few key principles of this strange quantum world.
Okay, I'm ready for the challenge. Lay it on me. What are these mind-bending principles that make quantum computing possible?
So there are four key principles that we need to wrap our heads around: superposition, entanglement, decoherence, and interference.
Okay, let's start with superposition. What does it mean for a particle to exist in multiple states at the same time? That sounds kind of impossible.
I know, right? It's one of the things that makes quantum mechanics so counterintuitive. But imagine this. Think of a qubit, the quantum equivalent of a bit, as a coin that can be both heads and tails at the same time. That's superposition.
So it's not just heads or tails, but a blend of both. That's wild. How does that even work?
It's a bit like a musical chord. It's not just a single note, but a combination of multiple notes played simultaneously. A qubit can exist in this blurry state of multiple possibilities until we measure it.
Okay, I'm starting to get a glimpse of how this could lead to immense computing power. But what about entanglement? That sounds even weirder.
Entanglement is definitely one of the most mind-boggling aspects of quantum mechanics. Imagine two of these qubits that are linked in a special way. Measuring the state of one qubit instantly determines the state of the other, no matter how far apart they are. It's like they're connected by an invisible thread.
That sounds almost spooky.
Welcome to
So,
AI
the act
Podcast,
of measuring
New
one
Tech,
qubit
your
influences
ultimate
the
destination
other,
for
even
the
if they're
latest and
miles or
greatest in the
light years
world of
away.
technology.
Exactly. One of the things that
Hosted by an
Einstein called
intelligent...
spooky action at a distance. And this interconnectedness between qubits is a key ingredient in the magic of quantum computing.
Wow, that's seriously mind-blowing. Okay, so we've got superposition and entanglement. What about decoherence? Does that have something to do with those quantum states collapsing?
You're right on the money. Decoherence is like the kryptonite to the quantum world. It's when a quantum system loses its delicate superposition and collapses into a definite classical state, a 0 or a 1, because it interacts with this environment. It's like that musical chord suddenly resolving into a single note. All the harmony is lost.
So keeping those qubits isolated from any disturbances is crucial then, like protecting them from the noise of the outside world.
Precisely. And that's one of the biggest challenges in building practical quantum computers. They often need to operate at extremely low temperatures, close to absolute zero, to minimize those pesky environmental interactions.
Okay, so we're talking about some seriously cold conditions. All right, we've covered superposition, entanglement, and decoherence. What about our final principle, interference? How do these quantum states actually interact with each other?
Think of two ripples spreading out on a pond. When they meet, they can either reinforce each other, making a bigger wave, or they can cancel each other out, leaving the water flat. That's inference.
So interference is about manipulating the probabilities of different outcomes, making some more likely and others less likely. Is that how it works in the quantum world?
Exactly. It's a bit like steering those quantum waves, guiding them towards the desired solution. And this ability to manipulate interference is crucial for designing those all-important quantum algorithms.
Got it. Now, let's dive a little deeper into those qubits. They're the building blocks of quantum computers, right? But how do scientists actually create them? I mean, are we talking about trapping subatomic particles?
Well, there are a few different approaches being explored, each with its own advantages and challenges. One promising method uses superconducting circuits. They're essentially tiny loops of wire that are cooled down to extremely low temperatures, close to absolute zero, where they exhibit those special quantum properties.
I'm sensing a theme here. Keeping things cold seems to be essential for quantum computing.
It's one of the key challenges. Another approach uses trapped ions, where individual atoms are held in place using electromagnetic fields, kind of like suspending them in midair. These trapped ions have the advantage of being incredibly stable and maintaining their quantum states for a longer time.
So it's a trade-off then. Different types of qubits with different strengths and weaknesses.
Exactly. There are also quantum dots, tiny semiconductor structures that can trap single electrons, and even photons, particles of light, which are being explored for quantum communication and cryptography. And don't forget, neutral atoms.
Wow, it's fascinating how researchers are exploring all these different avenues, but how do these qubits actually change the way we solve problems?
The IBM article has this really cool analogy about a maze. Imagine you're trying to find the exit of a maze. A classical computer would have to explore each path one at a time, systematically but slowly.
So a quantum computer, on the other hand, could explore multiple paths simultaneously. Is that the advantage here?
You got it. It's not that it physically travels down multiple paths. Instead, it uses those principles of superposition and interference to evaluate many possibilities at once, finding the solution much more efficiently.
That's a really helpful visual. Now, what about the software side of things? I imagine programming a quantum computer is completely different from programming a classical computer.
You're absolutely right. We need a whole new way of thinking about algorithms. Quantum algorithms are specifically designed to exploit the unique properties of qubits, those superpowers we talked about earlier, enabling them to perform calculations in ways that classical computers just can't.
So can you give us an example of a real-world problem that these quantum algorithms could tackle? Why is everyone so excited about this technology?
One of the most famous examples is Shor's algorithm, developed by Peter Shor back in the mid-90s. It has the potential to factor large numbers exponentially faster than any known classical algorithm.
Okay, but why is factoring large numbers such a big deal?
Well, it turns out that many of our modern encryption systems, the ones that keep our online transactions secure, rely on the difficulty of factoring large numbers. Shor's algorithm, running on a sufficiently powerful quantum computer, could potentially crack these codes wide open.
So quantum computing could have major implications for cybersecurity, both good and bad. It's a bit unsettling, but also incredibly fascinating. So what other fields could benefit from these quantum algorithms besides, potentially breaking the internet?
The possibilities are really vast. In drug discovery, for instance, quantum computers could be used to simulate the behavior of molecules with incredible accuracy, allowing us to design new drugs and therapies much faster and more effectively.
So we're talking about potentially developing treatments for diseases that are currently incurable.
Exactly. And in material science, quantum simulations could lead to the discovery of new materials with properties that we can only dream of today. Imagine superconductors that operate at room temperature, revolutionizing energy transmission, or ultra-efficient solar cells that capture almost all of the sun's energy.
It sounds like these advancements could completely transform the world as we know it. But with all this potential, I'm
Welcome
guessing
to
there must
AI
be some pretty
Podcast,
big
New
challenges.
Tech, your ultimate
absolutely right.
destination for
As
the
with any
latest and
emerging
greatest in the
technology,
world of
quantum computing
technology.
faces its own set
Hosted
of
by an
hurdles and
intelligent.
questions.
So let's dive into those challenges. What are some of the major obstacles that researchers are trying to overcome?
One of the biggest challenges is scaling. To tackle more complex problems, we need to build quantum computers with more qubits, hundreds or even thousands of them. But as you add more qubits, it becomes exponentially harder to maintain their stability and control. It's like trying to keep a room full of butterflies perfectly synchronized.
That sounds incredibly difficult. So it's not just about adding more qubits, but also making sure they can all work together harmoniously.
Exactly. And it's not just the processors themselves that need to scale up the entire supporting infrastructure, including the cooling systems, the control electronics. Everything needs to grow as well.
It sounds like a monumental engineering feat. And what about that decoherence issue we talked about earlier? Is that still a major roadblock?
Absolutely. Decoherence is a constant battle in the quantum world. As those quantum computers become larger and more complex, they become even more vulnerable to environmental noise, which can disrupt those delicate quantum states.
So, how are researchers trying to combat this decoherence villain? Are there any strategies in place to protect those fragile qubits?
Well, one promising approach is quantum error correction. It involves encoding quantum information redundantly, spreading it across multiple qubits to protect it from errors caused by decoherence and other sources of noise.
It's like building a fortress around those qubits, shielding them from the chaos of the outside world.
That's a great analogy. But it's not just about the hardware. There's also a constant need for discovering new quantum algorithms. We have a few powerful ones like Shor's algorithm, but we need many more to unlock the full potential of quantum computing.
It's like having this incredible new tool, but we're still figuring out all the ways we can use it.
Exactly. And those algorithms need to be written in a way that quantum computers can understand. We need better software tools and programming languages that make it easier for developers to create and optimize quantum software.
It sounds like a whole new frontier for software development with its own unique set of challenges.
And speaking of frontiers, where do you see this whole field of quantum computing heading? What does the future hold?
Well, IBM is certainly setting the pace with its ambitious roadmap for advancing quantum computing. They've set some pretty impressive goals, like achieving a 1,000 qubit system by 2026 and a million qubit system within the next decade.
Wow, those numbers are mind-boggling. 1,000,000 qubits, that's incredible. But are there any skeptics out there, people who think this whole quantum computing thing is just hype? Well, as with any emerging technology, there are always different perspectives. Some people point to the immense challenges of scaling these quantum computers and maintaining their stability and coherence.
So they're saying it's not a slam dunk. There are still hurdles to overcome.
Exactly. But the potential of quantum computing is so vast that even if we only achieve a fraction of what some predict, it could still have a profound impact on our world.
Well, on that note, I think we've covered a lot of ground in this first part of our deep dive into quantum computing. We've explored the mind-bending world of quantum mechanics, met the qubit, the superhero of quantum computing, and gotten a glimpse of how quantum algorithms could revolutionize everything from drug discovery to material science. But we've also acknowledged that there are challenges ahead, and there's no guarantee that quantum computing will live up to all the hype.
That's right. It's important to be both enthusiastic about the possibilities and realistic about the challenges.
But even with those challenges, it's clear that something extraordinary is happening in the world of quantum computing. So how do we actually measure the power of these quantum computers? And what does the future hold for quantum computing and its impact on our everyday lives? Those are questions we'll be exploring in more depth right after this.
I can't wait to delve into those questions. We're just scratching the surface of what's possible with this revolutionary technology.
It certainly feels like we're on the verge of a quantum revolution. But before we get ahead of ourselves, let's take a quick break and we'll be back to continue our quantum exploration in just a moment.
So, we've been talking about all this incredible potential of quantum computing, but how do we actually measure just how powerful these quantum computers are? I mean, are we just counting qubits or is there something more to it?
That's a great question. It's like, how do we even know if we're making progress? What are the benchmarks or metrics that scientists use to gauge the capabilities of these quantum systems?
Well, one of the key metrics is something called quantum volume. It's a concept that was developed by IBM, and it takes into account several factors, not just the number of qubits, but also things like the connectivity between the qubits and how long they can maintain their quantum states before decoherence sets in.
So quantum volume gives us a more
Welcome to
holistic
AI
view of a
Podcast,
quantum
New
computer's
Tech,
performance,
your
right? It's
ultimate
not just
destination
about
for the latest and
brute force
greatest in the
predictor, but
world
also
of
about how
technology.
well those qubits work
Hosted by an
together.
intelligent...
Precisely. It's a way to assess the overall computational muscle of a quantum computer. But like any single metric, it has its limitations. It doesn't tell the whole story.
So are there other ways to measure the performance of these quantum systems? What else are scientists looking at?
Right, so IBM has actually introduced a couple of additional metrics. One is called layer fidelity, and the other is CLOPS.
Okay. Those sound pretty technical. Can we break those down a bit? What do those metrics actually tell us about a quantum computer?
Sure. So layer fidelity is all about accuracy. It measures how precisely a quantum processor can execute a sequence of quantum gates, those basic operations that manipulate qubits. Think of it like checking the accuracy of each individual instrument in an orchestra.
So it's like ensuring that each qubit is hitting the right notes, so to speak.
Exactly. And then you have CLOPS, which stands for circuit layer operations per second. This metric is all about speed. It measures how quickly a quantum computer can execute a series of those quantum volume circuits.
Ah, so it's like assessing how fast the orchestra can play a complex symphony.
That's a great analogy. And these benchmarks are incredibly valuable for researchers and developers. They allow them to track the progress of quantum computing, compare different systems, and make informed decisions about hardware and software development.
It sounds like there's a whole science behind evaluating these quantum computers, not just building them.
Absolutely. It's an essential part of the process.
So, we've talked a lot about the potential of quantum computing, but also the challenges involved. It seems like there are still some pretty big hurdles to overcome before this technology becomes truly mainstream.
Right, and we've touched on some of those already, like scaling up the number of qubits while maintaining stability and coherence. That's a major engineering challenge.
Yeah, and as you mentioned, it's not just about the qubits themselves, but the entire supporting infrastructure has to scale up as well. The cooling systems, the control electronics, everything needs to grow.
And then there's that pesky decoherence issue. As quantum computers become larger and more complex, they become even more susceptible to environmental noise, which can disrupt those delicate quantum states.
So it seems like there's this constant battle between pushing the limits of quantum computing and protecting those fragile qubits from the outside world. How are researchers trying to address this?
Well, they're developing sophisticated techniques for quantum error correction. It's basically a way to encode quantum information redundantly across multiple qubits, so that if one qubit gets knocked off course by decoherence, the information can be recovered from the others.
Welcome
a
to
safety
AI
net for
Podcast,
precious quantum
New
systems.
Tech,
Exactly,
your
and
ultimate
it's a
destination
crucial
for the
area of
latest and
research,
greatest in
because
the
without
world of technology.
effective error correction,
Hosted by
it
an
can be
intelligent...
extremely difficult to build large-scale, fault-tolerant quantum computers.
So it's not just about building bigger quantum computers, but also about making them more resilient.
Precisely. We need to protect those qubits from the ravages of decoherence.
But even with error correction, building practical quantum computers must require a massive collaborative effort, right?
Absolutely. It's not something that any single company or research group can achieve on their own. It requires expertise from multiple disciplines: physics, computer science, engineering, materials, science, you name it. It's a truly interdisciplinary field.
And it's not just about the hardware either. Didn't you say earlier that programming these quantum computers is a whole different ball game?
Oh, for sure. We can have the most powerful quantum computer in the world, but without the right software and algorithms, it's basically just an expensive paperweight.
So what's happening on the software front? What are some of the key areas of focus?
One of the biggest areas of research is in developing new quantum algorithms. Right now, we have a few powerful algorithms, like Shor's algorithm for factoring numbers, but we need a much wider range to tackle all sorts of different problems.
So we need to expand the quantum software toolbox, so to speak.
Exactly. And we also need better software tools and programming languages that make it easier for developers to write quantum programs. Right now, it's still a pretty specialized field.
Yeah, I imagine programming a quantum computer is not something you just pick up overnight. It's like learning a whole new way of thinking.
And then there's this growing recognition that quantum computing won't necessarily replace classical computing entirely. Instead, we're probably heading towards a future of hybrid computing, where quantum computers work alongside classical computers, each doing what they do best.
So it's more of a collaboration than a competition.
Exactly. Classical computers are still really good at a lot of things, and they'll continue to play an important role. But for certain types of problems, particularly those involving complex simulations or optimization, Quantum computers have the potential to be game changers.
So it's about finding the right balance, right? Letting each type of computing shine in its own way.
Precisely. And it's important to acknowledge that not everyone is gung-ho about quantum computing. There are some people who are more cautious, even skeptical about its potential.
So it's not all sunshine and roses, then. There are some folks who think this whole quantum computing thing might be overhyped.
Well, there are always going to be different perspectives. And it's healthy to have those dissenting voices. They force us to question our assumptions and to be rigorous in our thinking.
Yeah, it's good to have a bit of skepticism to keep things grounded.
Absolutely.
Okay.
And, the truth is, we don't know for sure what the future holds for quantum computing. It's still a relatively young field, and there are many challenges ahead. But the potential is certainly enormous, and the progress that's been made in recent years is truly remarkable.
So it sounds like it's a field that's worth watching closely.
Oh, absolutely. It's one of the most exciting areas of science and technology today.
Well, we've explored the incredible potential of quantum computing, the challenges researchers are facing, and even the voices of skepticism. But what does all this mean for us, the everyday folks who may not be physicists or computer scientists? How could quantum computing actually impact our lives?
That's a great question, and it's one we'll be exploring in more depth in the next part of our deep dive. But let me just say this. The impact of quantum computing could be as profound as the internet revolution. It has the potential to touch nearly every aspect of our lives, from the way we communicate to the way we treat diseases, and even the way we understand the universe itself.
Okay, now that's a bold statement. I'm definitely intrigued to hear more about how this quantum revolution could reshape our world. But first, let's take a quick break. We'll be right back to continue our quantum exploration in just a moment. Okay, so we've covered a lot of ground in our quantum journey so far, the mind-bending science, the amazing potential, and the very real challenges that lie ahead. But now, let's bring it all home. How could this quantum revolution actually touch our everyday lives? It's kind of hard to imagine, right?
It's easy to get lost in all the technical details and think of quantum computing as something happening in some far-off lab. But its impact could be as transformative as the internet. Remember, back in the early days, the internet was this niche thing, mostly for researchers and techies. Now it's completely woven into our lives. Quantum computing has that same potential to reshape the world around us.
That's a pretty powerful comparison. So can you paint us a picture? How might quantum computing actually change things for everyday people? What are some real-world examples?
Absolutely. Let's start with healthcare. Quantum simulations could completely revolutionize drug discovery. Imagine being able to design drugs that are perfectly tailored to your individual genetic makeup, or drugs that target cancer cells with incredible precision, leaving healthy cells unharmed.
Wow, that would be incredible. Personalized medicine, targeted therapies. It sounds almost like science fiction. Are we really talking about making those kinds of breakthroughs?
It's closer than you might think. And it's not just healthcare. Think about materials science. Quantum computers could allow us to design materials with properties that we can only dream of today. Imagine super-efficient solar panels that capture almost all of the sun's energy, or lightweight, ultra-strong materials
Welcome
that
to AI
revolutionize everything
Podcast,
from
New Tech,
airplanes
your
to
ultimate
buildings.
destination for the
amazing to think
latest
how
and
these
greatest in the
advancements
world of
reshape our
technology.
And what about
Hosted
artificial
by an
intelligence?
intelligent
AI. Everyone's talking about AI these days. Could quantum computers give AI a massive boost?
That's a really hot area of research right now. Quantum machine learning algorithms have the potential to analyze huge data sets much faster and more effectively than classical algorithms, leading to more powerful and sophisticated AI systems.
So quantum computing could accelerate the development of AI, but is that necessarily a good thing? I mean, there are a lot of concerns about the potential downsides of AI, right? Like, what if it gets too smart and takes over the world?
Those are important questions, for sure. Like any powerful technology, AI has the potential for both good and bad. We need to have thoughtful conversations about the ethical implications and make sure we're developing these technologies responsibly.
So it's like we're standing at the edge of a new frontier, full of possibilities, but also some potential dangers.
Exactly. And that's why collaboration is so important. Quantum computing isn't something any one country or company should control. We need a global effort, bringing together brilliant minds from all over the world. Physicists, computer scientists, engineers, ethicists, policymakers. Everyone needs to be involved in shaping the future of this technology.
It sounds like we need a kind of global quantum alliance to make sure this technology is used for good.
I think you hit the nail on the head. It's not just about the technology itself. It's about how we use it, the values we embed in it, and how we share the benefits.
Well, we've covered a lot of ground in our quantum deep dive, exploring the mind-blowing science, the game-changing potential, and the challenges that still lie ahead. As we wrap things up, what's the one key message you hope our listeners take away from this conversation?
I want them to remember that sense of wonder. Quantum computing is pushing the boundaries of human knowledge. It's showing us that the universe is far stranger and more interconnected than we ever imagined. And it's an invitation for all of us to engage with this amazing journey of discovery.
I love that. It's a reminder that we're all part of this grand adventure of exploring the universe and unlocking its secrets. And on that note, we've reached the end of our quantum journey for today. But it's really just the beginning, so keep those brains buzzing, stay curious, and who knows, maybe you'll be the one to make the next big quantum breakthrough.